Hello everybody. So, we have discussed so far that working stress method as per IRC 21 and also which is applicable for IS 456 2000 also. Next we have discussed on IS 456 the limit state method, because I thought that you are introduced first with that IS 456 to 2000. Those who are old, maybe you are using that IRC 1978. First time actually the limit state method was introduced in 1978, IS 456. Later on IS 456 2000, that is actually modified certain clauses. Now we shall go for it. The next one, that is our lecture 8, that reinforced concrete road bridges, lecture 8, that we shall consider. And now we shall go for limit state method, that what is the general one, IRC 112 2011, and then we shall consider the Flexure, and later on we shall go for your CR. Whenever we solve the problem, that time we shall go for CR, because I thought that certain orientation is required regarding that your say concrete, then it will be easier to know that how we are going to apply that. And also very interesting that when you are having working stress method as well as limit state method, then it will be very interesting to know the difference, or rather you will find out there is no such difference, only few parameters are being changed and then the whole thing is working fine. That is my idea, that is the one my understanding. So, coming to this one here, limit state method IRC 112 2000, whatever that code says, let us see limit state of collapse, that finally we shall discuss, and summary and references. So, limit state method IRC 112 2011. So, this is the one clause I have taken this particular one here, that I have taken the relevant clauses are there only. So, the bridge as a complete structural system and its structural elements should perform their functions adequately and safely with appropriate degrees of reliability during design life and during construction. So, this is the one which is given in that clause 5.1.1, that it is given here. So, what it says, again let us repeat once more, as a complete structural system and its structural elements should perform their functions adequately and safely with appropriate degrees of reliability during design life and during construction. So, not only during design life, but as well as during construction also, that we should take care of that. It should withstand all actions consisting of applied and induced loads. There should be a gap here, induced loads as well as environmental influences liable to occur, retaining its structural integrity, and also withstand accidental loads, as for example, barge impact, vehicular impact, it happens, and earthquake loads without causing damage which is disproportionate to the causative event. So, this is your another one, that part of that. Adequacy of performance is defined in terms of serviceability, safety, durability and economy. So, you have to consider many aspects, that whether the performance is adequate or not, whether it is deficient in some other aspect or not, that you have to find out from all aspects, serviceability, safety, durability and economy also. There are certain things, as I have told you, actually the reliability, other things that is coming into picture always. So, and then I thought it is worth to repeat that one, whatever available in that particular code, that let us see this particular one, whatever it states. The term degree of reliability is used to indicate the acceptability low level of probability of failure in meeting the expected performance during a specified period time. This dot will not be there. during a specified period of time. Determination of the reliability measured in terms of statistical probability requires knowledge of statistical parameters which define loading and material strength. As I have told you in the fifth one lecture, that we have shown you that your say reliability, certain kind of thing that we are telling, just to tell you that something like that we are getting. Let us use another color so that it will be clear. Generally we use Gaussian distribution on normal distribution. This case we are having certain value here, this case we are having certain value here. So, this particular one, now whatever we are doing this particular one here statistically, whatever distribution, because it will not happen that only one single value we shall get it every time. We shall get different values, but that value will follow certain pattern, certain actually distribution. That distribution most of the cases it happens normal distribution. So, that particular one we have to consider here. So, that is why you have taken that knowledge of statistical parameters, how it is actually behaving statistically, that also you have to know. That is for the loading also, for the material strength also. The data together with knowledge of structural models of resistance enable evaluation of structural performance in probabilistic term. At the present state of knowledge, determination of reliability is possible only in limited load cases for simple structures. That is true, of course. The code therefore strives to achieve the desirable degree of reliability by approximate methods based upon a combination of the following. What are those combination? Known statistical parameters describing properties of materials and actions, deterministic models of structural behavior, the international practices and past experience of acceptable, unacceptable performance of structures, partial factors for actions, resistance, models based on calibration and rationalization of existing international practices. So, this is the one I have taken from IRC 112, this particular one that you can see, this particular one there itself. The response of the structure when subjected to different magnitudes of loads lies in different states. Limit states are defined as limits of domains beyond which the structure does not meet specified performance criteria. This is the one we can say. In limit state philosophy of design, various boundaries of acceptable unacceptable performance are defined together with the circumstances in which such performance are expected. So, this is the one that we call it a limit state of philosophy, the various boundaries. So, we shall give that different boundaries, that is the one, that is why we tell it a partial safety. We are giving different boundaries and we are working with that particular one domain. So, that way you can consider, we are giving a boundary for say your steel, for concrete, for loading, for deflection, like that we shall give different boundary that we shall give. It is not the one only unique criteria that only it will give stresses. Now, coming to this one here, two basic groups of limit states are considered, ultimate limit states or ULS. These limit states cover static equilibrium and failure of structural elements or structures as a whole when acted upon by ultimate design loads. And the second one we are having serviceability limit states SLS. These limit states deal with the condition of the structure subject to influence of serviceability design loads. These conditions include level of internal stress, fatigue, failure, deflection, damage to structural elements such as cracking and discomfort to users due to vibrations. So, these are called serviceability limits. So, one is ultimate limit state, another one serviceability. The limit state of collapse, which is known at in IS 456, and limit state of serviceability, here we say ULS and SLS. The representative values of actions and combination of actions representing different design situations are defined. The representative values of loads are modified by using load factors for each of the basic limit states which are then combined using combination factors. The combination factors take into account the probability of simultaneous occurrence of loads. So, that is why that wind and earthquake we generally do not take together. So, that is why that combination you have to consider that occurrence of the load, on the basis of that actually you have to decide. The response of the structure is calculated using principles of mechanics and simplified established models describing behavior of concrete members. These methods also account for inherent geometric variations which are kept within acceptable construction tolerances. The response of the structure is required to lie within acceptable domain for different combinations of actions. The structure designed by following this philosophy and constructed by satisfying other stipulations of the code are deemed to meet the general performance requirements, which already we have discussed in the very beginning of this lecture, that is clause 5.1.1, which we have told you earlier, and that is the one. Just to repeat once more, this is the one already we have given, that particular one. I am not reading again, but this is the one already we have given. Just for continuity I am showing it here. So, I have just simply read this particular one here, but the basic idea that particular one, what I would like to say, that we are having different parameters, and for each parameter we are having different partial safety factors. Not only that, the load combination that will be dependent on the simultaneous occurrence of that load, that if it does not occur at the same time, that then we shall not take that particular combination with some other load. As I pointed out, that earthquake load and wind load, that we assume that it will not work together. We can take it that particular one there, but for an important structures, but then it will be very very rare situation, and in that case we can omit that particular combination, that taking together earthquake and wind. Now, ultimate limit state ULS, the limit state of equilibrium, when subjected to various design combinations of ultimate loads, the bridge or any of its components considered as a rigid body shall not become unstable. So, this is the one equilibrium, that as a whole it should be in equilibrium position. And limit state of strength, the bridge or any of its components shall not lose its capacity to sustain the various ultimate load combinations by excessive deformation, transformation into mechanism, rupture, crushing or buckling. So, that is the one we can consider that as a part of limit state of strength. The next one, this is called under ultimate limit states. So, limit state of equilibrium, that is we are not going to internal stresses, that from externally whether it is in a stable condition or not, equilibrium condition. Then limit state of strength, we are considering that on the stresses on the basis of that. Serviceability limit states SLS, limit state of internal stress, the internal stress developed in the materials of structural elements shall not exceed the specified magnitudes when subject to combination of serviceability designations. The stresses are to be estimated using resistance models to represent the behavior of structure as stipulated in the code. So, this is the one we shall consider that for internal stress. Limit state of crack control, the cracking of reinforcement partially pre-stressed and pre-stressed concrete structures under serviceability load is kept within acceptable limits of crack widths in such a way as not to adversely affect the durability or impair the aesthetics. So, this is the one we can consider here, that not only durability, but as well as the aesthetics also that you have to consider. Alternatively, the control of cracking is deemed to be satisfied by following restrictions on amount and spacing of reinforcement. So, that means we can give restrictions on amount of and spacing of reinforcement, that also. Next one, SLS, we are having actually limit state of deformation. Deformation of the bridge or its elements when subject to combination of design actions shall not adversely affect the proper functioning of its elements, apportionates and then riding quality. Deformations during construction shall be controlled to achieve proper geometry of finished structure. So, this one it comes under deformation. Then the very important one, limit state of vibration. For footbridges or component of bridges specifically designed to carry footway loading, the direct variation of vibration limits is required, for which specialist literature may be referred. For specialist types of bridges and their components, dynamic effects under action of wind are required to be calculated and verified to be within acceptable limits. Model tests are required under certain circumstances. For other types of bridges, the limit state of vibration under subversive load combination is deemed to be satisfied by limiting deflection of elements. So, this is the one that whatever available in that IRC 112, from there I have taken it. So, that you can find out there also, because whatever the checking we have done. This is another important factor, limit state of fatigue. The bridge or any of its components shall not lose its capacity to carry design loads by virtue of its materials reaching fatigue limits due to its loading history. For carrying out fatigue verification, specialist literature may be referred. So, this is the one we have, that one here say limit state of fatigue. So, we can just simply I can once more repeat. So, ultimate limit states there are two, equilibrium and strength. Then service limit says that internal stress, crack control, deformation, vibration and fatigue. So, these are the things available, we have to check all those things that we have to find out. So, coming to this one here, that limit state of collapse, that flexure, let us see what is available there. We are using the same curve, this particular one we are considering here and this particular one we are considering here, the same curve we are considering here. So, we can say FCD, this is the value of FCD, alpha FCK by gamma m, alpha equal to 0.67, gamma equal to 1.5 for basic and seismic combination, 1.2 for accidental combination. So, this is the value that we can consider, that one gamma m we can consider here, that 0.67 and then 1.5 then 1.2, that means here IS 456 there it is written clearly that you take 1.5. If you take it 1.2, that means we are taking little more value. Otherwise, if you take 1.5, so it will come that value, this particular value it will come here, that 0.45 or 0.44444, 0.45 FCK, that will come here. And this is the formula, that particular one here, because we are having two parts, this part and then this part. So, this part is constant and this part parabolic. So, FCD 1 minus 1 minus epsilon c by epsilon 2 to the power n, and this is epsilon 2 to epsilon n. So, that means here we are getting this portion constant and this portion we are considering parabolic. So, one portion we are considering constant and one portion we are considering here that parabolic, that we are considering here, and that formula we are getting. So, that is why n is equal to 2. So, that code it is given in the code, that what is the value of n, that is also given in that IRC 112. Here we have taken for up to concrete grade M60, that n equal to 2, epsilon C2 which I have not mentioned, that particular this is 0.002, that particular one is written, and 0.0035, and obviously it is up to M60 according to IRC 112. Now, the coming to that one, that we have started actually the discussion on the IS that IRC 21 or IS 456, where we have used that your working stress method. Then we have gone to that limit state method according to IS 456 2000. Now we are telling something, though we are using the same stress block, but here the code says the parabolic rectangular stress strain block is of general validity for all design situations. That means, whatever we have done in IS 456, that is also applicable here. It is not like that it is not applicable, it is also equally applicable. However, simplified equivalent stress blocks such as rectangle or bilinear may be used for design purposes where the net results are sufficiently accurate. Here they are telling net results are sufficiently accurate. There they have told the substantial agreement. So, this is your one case, actual one, then you are reducing that value, that is possible. Now, coming to this particular one here, what I would like to say that this is the one we are getting here. So, if we consider that if we consider this particular value, that your say area of concrete and this is area of steel, this is the one that effective depth, x is the distance here, epsilon cu3 epsilon s, that is for the steel and concrete, that value you can get it from the table, and this eta fcd lambda x and fc. So, this particular one we can consider that for fck less than equal to 60 MPa, lambda will be equal to 0.8, eta equal to 1 and fcd equal to 4 by 9.445, that is the one. So, what we are getting out of it, this particular one is very, very important here, what we are getting out of it. So, if you really say this particular one here, just to give you idea, let me draw it in a rectangular format. So, what we can do it here, this is our strain diagram. So, epsilon and epsilon s, this is our neutral axis. So, what we can do it here, now recall our objective is that here we would like to make a parabolic distribution. From parabola, just see why I have taken this one, this is the one parabolic one. This area I would like to make it, which is 0.364 FCK, that particular one we are having. So, this value if we write down here, so what we can do it here in this case, please note that figure which we have taken from the code, that here that lambda x, that means I have reduced this value. So, I have considered this one as say lambda x, that we have taken here. So, this is 0.364 FCK x by d BD. So, if I take this cross section, then how much will be the lambda then? So, lambda x into 0.45 FCK will be equal to 0.364 FCK. So, lambda will be equal to 0.8. So, we shall consider the lambda that 1.8, then only I can get the same area lambda 0.8 eta 1 FCD 4 by 9.445. So, we can find out these values that we can find out here, that we can do it. So, this is the one I would like to tell you that whatever value you are getting it here, that way we can consider here. Now, coming to this one, so coming to this one here, so this one so this is Z. So, I can write down mu 0.8x lambda equal to 0.8 into B into 0.445 FCK D minus 0.5 into 0.8 x. So, this portion is half of 0.8 x, because this is the 1.8 x, half of 0.8 x, that we shall get it here, that we can find out this particular one we can find it. So, from this equation, whatever we are getting here, from that equation we can find out that your value. So, I can say Z equal to D minus 0.4 x, because half of this is 0.4 x. So, we can write down x 2.5 D minus Z, and as usual I can write down m 0.36 FCK B 2.5 D minus Z So, this is the equation we can get it here. So, m equal to 0.9 FCK B Z D minus D square, sorry Z square, and K mu by this particular one we can consider here, just a minute. So, we can write down this one here, that m by FCK BD square equal to 0.9 FCK Z by D minus 0.9 FCK Z by D whole square, and from there again we can find out that equation we can again find out from this particular one mu by FCK BD square 0.9 FCK Z by D minus 0.9 FCK, and we can find out this equation again, that we can consider here Z by D whole square minus Z by D plus 1.11 K equal to 0, K equal to mu by FCK BD square. So, we can find out here what I mean to say. Earlier we had 1.11 K, and then we can get this one Z by D whole square. So, from there we can find out that value of Z by D, we can solve that value of Z by D, and from there we can find out that again the same type of equation we can do it, and then we can go for it, and which will give us the solution of the same format Z by D whole square minus Z by D plus 1.11 K equal to 0. From there I can get the value of Z, because earlier whatever I have told you here, the equation. So, here finally we can get that equation here, that J we can say again 0.5 plus root over 0.25 minus 1.11 K, like that we can get it here. This is the value we can get it. That means, here earlier whatever value we have got it here and 1.15, and here you are getting here the value of 1.11. And similarly, working stress method also you will come, then also you can get it the same way we can find out. So, that is why I would like to say that I would like to say that working stress method, again this particular one here whatever we have discussed that on the very beginning. So, sigma CBC, which is nothing but I can say FCK by 3, and similarly K also we can make it. So, all the terms if we make it here, we can get the same expression, that value, that J also we can make it there. So, that is why I am telling you that working stress method whatever given in IRC 21 or IS 456 or limit state method exclusively for IS 456 or the simplified method with the rectangular block, whenever we are going for say IRC 112, you will find out the expression remains same, only in the few parameters you are going to change that particular one, and from there you can find out how much is actually changing in your say depth of the beam or your say reinforcement. So, this is the one just to give you certain orientation before going to the actual problem. So, design the solid slab or RCC T beam. We are just given that this particular one, that you would say orientation on the reinforced concrete design, and previously we have done that what about the loading to be considered and whatever your that dimension of the bridge you have to consider, the geometry. So, those things we have discussed. So, in that way we are now at least ready to go for design. So, we shall start that first problem with the solid slab, and then we shall go for RCC T beam. As I have told you, the objective of the course is that we should know that how to design that particular one, what are the steps you have to consider, what are the methods you have to consider, and what are the loading combination you have to consider, that we shall solve with that problem. Thank you very much.